In this video, we're going to look at the little bit more detail at the reactions of alcohols with strong acids, okay? And we mean HX specifically. So when you treat an alcohol with one of these hydrohalic acids, a rapid reaction ensues, leading to an alkyl halide right here and water, okay? In this reaction, our X group can be chlorine, bromine, or iodine, but it cannot be fluorine. Our reaction rate in most cases is going to be what we call a first order reaction. It depends on the concentration of the alcohol and not the concentration of the acid. If we look at the relative rates here, when we have a tertiary alcohol, the reaction is much faster than any other type of alcohol. This is faster than secondary, which is faster than primary or methyl. The reaction is just generally not efficient with primary or methyl halides. In order to address all these issues, we're going to look at something called the reaction mechanism, which is a detailed description of the reaction, including all the reactive intermediates and all of the transition states. Okay? And in this class, we will never look at a mechanism as deeply as we do this one. We're going to use this reaction mechanism here as the foundation for a lot of mechanistic principles that we're going to apply to other reactions as we go through the class. Okay, so how does this reaction go? First, let's look at some basic reaction dynamics. Okay, if you recall from the discussion of potential energy diagrams, we looked at how reactions proceed. This is a good example here of something we call an endothermic reaction. Okay, so when reactions proceed, they transition from reactants to products. Okay, so let's just put that in here. This is reactants. And they go to products, okay? But it's not a smooth transition. We don't just slowly gain energy here in this endothermic reaction as we transition from reactants to products. In reality, as the reaction progresses, it produces much higher energy intermediates. Okay, so the highest energy point along the reaction pathway is this point right here, which we're going to call a transition state. And the amount of energy you have to put into the reaction to make the reactants convert to the transition state is called the energy of activation right here. Okay? And if the reaction were reversible, in magenta here, we would have the energy of activation for the reverse reaction. Okay, what we find here is that the energy difference between reactants and products is related to the equilibrium constant through delta G equals minus RT ln KEQ. But we find that the energy of activation is actually related to the reaction rate, okay, through this equation right here. Okay? All right, another interesting facet of reaction dynamics is something called the Hammond postulate, which is stated right here. And this is that the transition state looks more like the species that's closest to its in energy. In an exothermic process, the reactants are closer to the transition state, while in an endothermic process like this one, the products are closer in energy to the transition state. Okay, so here's the energy of the products, here's the transition state. The energy of products is closer. Okay, energy of reactants is much farther away from the transition state. Okay, all right. Okay, so let's see what this means as far as the mechanism goes. this is the generally accepted mechanism, and I'm demonstrating it here on the reaction of a tertiary alcohol with hydroiodic acid. Okay, this reaction of tertiary butyl alcohol with HI produces tertiary butyl iodide and water. Okay, step one is basically the last thing on the previous video. There's a acid-base equilibrium, much like the Arrhenius equation, except that an alcohol is replacing water in the Arrhenius equation. Okay, I have this arrow going to the right, and this is just an educated guess here, but we should understand that if HI is a strong acid, it would react with water and go to the right, so it ought to react with an alcohol and go to the right as well. In step two, we're losing water. Okay, and we're generating a carbocation, a positively charged carbon, and water. An important thing to note here in step two is that iodine is still here. It's not shown because it's not really part of step two, but it's watching this all this stuff happen. Okay, I'm calling this an endothermic or an unfavorable reaction, and there's a lot of things about this that don't look so good. Primarily, let's just look at this intermediate, the species right here. We'll look at it in more detail a little bit later. Okay, this is the carbocation. There's only 6 electrons at that carbon. There's no octet. Okay. And what we're going to find as we discuss carbocations is that they're typically very unstable compounds. The carbocation here exists only as an intermediate. We're going to call this a reactive intermediate. Okay. And in the final step, step 3, the iodine reacts, I- reacts with a carbocation to generate the other product of the reaction. I have this as being a hugely exothermic reaction, and this is probably quite understandable. Everything gets an octet, all the charged species disappear. There's just nothing not to like about step 3. Okay. Here also, if we look at this mechanism, we can answer one of the limitations that we noted in the first slide. Why does hydrofluoric acid not work? And it doesn't work because it's not a strong acid. Okay, HF is a much weaker acid than HI. This reaction here goes predominantly to the left. So because step 1 does not happen very well with HF, none of the other steps happen. And so that's the first limit that we see on the reaction. Okay, so if we look at step 1, I'll just summarize what we said previously. It's exothermic and it's fast. This can be inferred from the Bronsted-Lowry equation. We're merely substituting ROH for water. And we can regard this step here really as a pre-equilibrium. It's something that just occurs almost spontaneous, or it does occur spontaneously when we add acid to the alcohol. Step 3 is also very fast and very exothermic, and it's the only species that does not have an octet. The carbocation gets one in this step, and we eliminate all of the charged species. Step 2 is really the most important step of the reaction. This is the slow step of the reaction, okay? And the reaction can never go faster than its slowest step. We're going to call this step here a big name, the rate determining step, or RDS, okay? That's what the abbreviation RDS stands for. Okay? The reaction can, we have to look at the rate determining step to determine what is the overall rate of the reaction. Our chemical intuition basically suggests that this step is not as favorable as the other ones because it's the step where we generate the only species lacking an octet, the carbocation. The rate effects that we noted a few slides ago can be explained by this step. First, the rate. Why is the rate first order? Okay, the rate is first order because in step 2, there is no iodine. Notice that it's just a bystander here. It is not involved in the reaction equation. Okay, so only water, or more accurately the protonated alcohol, appear in the rate equation. Okay, the rate is also will depend on how easy it is to form the carbocation. Okay, the easier it is to form the carbocation, the more facile is going to be this step right here. Okay, and when we discuss carbocations, we're going to see that alkyl groups stabilize carbocations, and that this accounts for the higher reactivity of tertiary alcohols. Okay, so here's a potential energy diagram for the reaction. Okay, what we see is that there's 3 steps, thus there are 3 transition states. Transition state for step 1, transition state for step 2, and transition state for step 3. Okay, here are the activation energies for those steps. And notice how the activation energy for step 2 is huge compared to the activation energies for step 1 and step 3. Okay, so we're going to have to look at step 2, and here's step 2 shown in greater detail down here. Okay, so here is step 2 blown up. Okay, so the Hammond postulate tells us that our transition state, which is right here in energy, is going to be something that looks kind of like the carbocation. I'll just guess at what the transition state here is, but it's something like that, where water is starting to leave, and when it's partially bonded, it's actually higher in energy than when they're completely separated. Okay. All right. So if we make the carbocation lower in energy, the activation energy is going to go down. So if we stabilize it by making it tertiary, it goes down. And if we destabilize it, this energy is going to go up. And this is all going to have major effects on the rate determining step of the reaction. Okay, another interesting point here. What's the difference between a reactive intermediate and the transition state? Okay, well, a reactive intermediate is what we call an energy minimum. Okay, so here's a reactive intermediate, ROH2. Here's a reactive intermediate, R+. In a transition state, is at an energy maximum. Okay, a reactive intermediate, there might be some conditions under which we could isolate it, because there's a barrier to the reactive intermediate turning into something else. But we could never have any hope of isolating a transition state because its transition to something else occurs without any sort of energy barrier. Okay, so let's look at the carbocation. This is the structure of the carbocation from the VS-EPR rules. It's sp2 hybridized. There's an empty p orbital. It's isoelectronic with a compound BH3, which, remember, a few lectures ago was the compound that we used to illustrate sp2 hybridization. Okay, if we compare isomeric compounds of the formula C4H9 plus, okay, we find that the most stable form is this form, where it's tertiary, and the least stable form is the primary carbocation. This one here we're going to refer to as secondary, and this is intermediate in stability. Okay, so the tertiary is the most stable or lowest energy. The primary is the least stable or the highest in energy. Okay, so alkyl groups are stabilizing a carbocation. How do they do that? They do it by something known as hyperconjugation. Okay, so in hyperconjugation, we're taking the electrons in the CH bond, okay, and we're donating them to the empty p orbital. We can look at this in a molecular orbital diagram over here. So we can describe the CH bond as being a sigma bond or an antibonding orbital. The p orbital would be empty. The CH bond would have 2 electrons. When we interact them like this, there's a net stabilization. And this accounts for the added stability of the carbocation. The more alkyl groups we have, the more hyperconjugating interactions we can have. Okay, it's important to note also that in this structure here, only this CH bond right here is participating in hyperconjugation. These two are not involved in hyperconjugation. Only the CH bond that's completely parallel to the p orbital can participate in hyperconjugation. So only this one, because it's parallel to the p orbital. Okay, here's a picture that I just lifted from the textbook. It's just showing some hyperconjugation interactions. Okay, so here's ethyl cation versus isopropyl cation versus T-butyl cation. Okay, they actually make the intellectual leap that this is starting to look like a protonated alkene or a protonated CC double bond. They use the resonance arrow. I'm not sure this is really resonance, but starting to look like it, as long as you don't move the bond too much. Okay, I mean, it all depends on is there a change in the connectivity? How bonded is that hydrogen? Okay, as long as there's some bonding, I guess it's technically a resonance structure. We're going to see how in the next chapter that's actually going to be quite an important concept. Okay, so here's a problem. Again, you should rank these. Okay, sorry, you should pause the video and go ahead and do this problem. I'm going to go through it right now. Okay, just so you should do it, then restart the video. Okay, so we're going to rank each compound in terms of its relative reactivity towards HI. We're going to rank the most reactive as number 1 and the least reactive as number 5, and put in numbers 2 through 4 where appropriate. Okay, so an important point here is that we're really looking at the carbocation intermediates that get left behind from the mechanism. So remember, the mechanism involves ROH with HI So all we have to really concern ourselves with was how these compounds are going to fare in this one step of the reaction. So what kind of carbocations are each of these alcohols going to lead to? Okay, looks like I picked a rather crappy place to put that picture. Sorry about that. But the one here on the far left, this is going to make a tertiary carbocation. Okay. This is going to make a primary one. Secondary. Tertiary. Secondary. Okay. And it's also a good rule. I told you about this a few days ago. When you have charged species like carbocations, don't draw the bond line diagrams in the presence or in the vicinity of the carbocation. Okay, so here are the types of carbocations. We know that the tertiary ones are the most stable. Okay, we could infer that because fluorine is electronegative, it's pulling electron density away, it's getting a partial positive charge to that carbon. Having two positive charges really close to each other isn't quite so good. Okay? Alright, so let's do the final ranking. We can probably say that the tertiary one without problems is going to be number 1, the tertiary one with a few issues is going to be number 2, and the primary one is going to be dead last. Okay, we can't really tell the difference between these two. They're both secondary. Rest assured, on an exam, I will not have any ties, okay? I'll always pick examples where there is a clear-cut difference in the relative stability. We're going to eliminate ties. So don't write that any two of them are tied on an exam. We're always going to pick examples where there's a clear-cut ranking order. Okay. All right. So the phrase electron donating group is going to be used to describe alkyl groups. Okay? And this is because they stabilize electron deficient species, i.e. carbocations. Carbocations we're going to refer as electrophiles or Lewis acids. The halogens that they're reacting with, is a nucleophile. Okay, when we get to primary and methyl halides, there's actually not really good yields of alkyl halide produced unless the halogen is iodine. We'll get into the explanation for that when we talk about chapter 8. But for example, the reaction right here, where we're taking 1 pentanol and treating it with HBr, is going to produce this in very low yield. Okay, so this is not a great reaction. It's also known that the kinetics for this reaction are a little different. It's a second order reaction. Okay. And it turns out that HBr does matter. So here's the proposed mechanisms for primary and methyl halides reacting with HX. Step 1 is exactly like step 1 is for tertiary alcohols. There's no difference there. In step 2, because this formation of the carbocation is so high energy, because it's really high energy, because this is just really not a very stable carbocation, it just doesn't happen. So what happens is that the bromine comes along and directly kicks out the water without there ever being a carbocation. Okay, so this is only a two-step reaction, and the rate determining step is our second step. Okay, one problem with organic chemistry is it's hard to explain everything in order. To explain everything accurately, you always have to bring something out of the future and say, we'll get back to it later. And this is the first case, I guess, of that. In Chapter 8, we're going to look at these substitution reactions in a much higher level of detail. Okay, so if we look at steps 2 and 3 with a tertiary alcohol, we have our rate determining step 1 and our product forms in the last step. Our rate here, because there's no iodide ion in the first step, is just this rate expression right here. And we call this a first order nucleophilic substitution reaction. We're going to use the moniker SN1 to describe that. Okay, step 2 is a reaction with a primary alcohol. Okay, so in step 2 of a primary alcohol, this is the only step we have. It's the rate determining step, and you see that both the bromide and the iodide are involved in the reaction. And this is a second order nucleophilic substitution reaction, and we're going to call this one SN2. We're going to revisit the concept of SN1 and SN2 in Chapter 8 in a big way. Okay, because these reactions don't really work that well for primary and secondary halides, alternative reagents have been created for carrying out this transformation. So if you want to turn a primary or alcohol or secondary or methyl into the corresponding chloride, the reagent of choice is not HCl, it's thionyl chloride. Thionyl chloride reacts with the alcohol to make the alkyl chloride, SO2 gas, and HCl gas. So for example, if we take this alcohol right here and treat it with SOCl2, we'll get the corresponding alkyl halide. And this is the way organic chemists are commonly going to write reaction equations. Other chemists call us sloppy because we don't balance the equations, but nobody would use this reaction here to make SO2. The only reason for doing this reaction is to make the alkyl halide. So we kind of focus on what's happening to the organic parts of the reaction equation. If you want to convert a similar type of alcohol into a bromide, the reagent of choice is phosphorus tribromide. Okay? So this reaction is going to make the alkyl bromide and phosphorus acid. If you look at the stoichiometry, every one of those PBr bonds is actually going to convert to a CBr bond. So the stoichiometry involves 3 alcohols and 1 PBr3. So in this bottom equation, if we take this alcohol and treat it with PBr3, we just expect to replace OH with Br and generate the product over there to the right. Okay, so here's a common type of equation that you'll see on exams, asking you to predict the product of a reaction or supply the missing information denoted by a question mark that's necessary to complete each reaction equation. In these reactions here, I want to add something that you'll see quite frequently, the benzene ring. The benzene ring is relatively inert in most of these reactions. In fact, for a while, we're going to be throwing benzene rings at you, but just don't do anything with them till we get to Chapter 11. Then we'll talk about their reactivity. Okay, So what's going to happen when this is, again, you should do this one and stop, pause it, and then see how your answers compare. All right, this first one, the OH group is going to just be replaced with Br. That's what we get. And the second one is a tertiary alcohol, HCl. This should be an efficient reaction for replacing the OH group with chlorine. This really isn't the whole story because this is really two compounds. We can have, there's the trans. And there's the cis. So there's really two products here. But by me drawing the starting material the way I drew it, it implies that we're not going to focus on the stereochemistry issue. Yes, it's there, but we're just not going to focus on it as far as this problem goes. If you really did it, you would find that you were isolating two different, or that you are making two different compounds. Okay, this one we're reacting a dialcohol with HI, and we're being very careful to add exactly 1 mole. What does this mean? Well, we're going to have to think about the selectivity. This is a tertiary alcohol, and this will go through a tertiary carbocation, whereas this is a primary alcohol. And this one would go through a primary carbocation, or would go through that SN2 pathway. Okay, remember our relative rates for this reaction. Tertiary faster than secondary, faster than primary. If we're very careful to control the amount of HI that we add, we're only going to get substitution at the tertiary alcohol, and that's the product that we should predict right there. Okay, what's the ideal reagent for turning that alcohol into that alkyl halide? The important thing to note is that it's primary, and that the ideal reagent is SOCl2. HCl would probably get you some partial credit, but it's, remember, not ideal. For turning a primary alcohol into a primary chloride, because, again, the intermediates are a little bit high in energy. Okay, I think this is, no, sorry, we have one more. Okay, here's a problem. Now, this is a very important problem. This is, write a mechanism for the transformation depicted below. And the mechanism really isn't that hard. It's just taking the mechanism we had before, and every place where you saw 3 methyl groups, you'll now have just 2 methyl groups and a benzene ring. Okay? And I actually sort of pointed that out to you here, that the benzene ring is unreactive. Okay, so when you write a mechanism, some important things you want to do is that you want to depict every intermediate, every energy minimum. Not every transition state, but you want to show every reactive intermediate. And you should also be sure that you use arrows in the proper way. Another important point in a mechanism problem is that we have to use only the reagents in the reaction equation. We can't bring external reagents out. So some people like to have OH minus doing things. Some people, well, here this reaction is not that complicated. I can't imagine what else you would want to put in here, but when you do a mechanism problem, always limit it yourself to what's in the reaction equation. Okay, if you need something else, whoever wrote the problem didn't write it correctly. Okay, so we have one step where we're going to protonate the alcohol. Here's another thing. Oftentimes when organic chemistry professors go to all the trouble of drawing a lone pair, they mean for you to use them. Okay, that's not always the case, but that's just a hint here. Okay, so this is going to give us this ionic pair, this ion pair right here, protonated alcohol and I minus. Okay, we're going to lose water. The CC bond, okay, right here, is going to become one of the lone pairs at water. Note we have two lone pairs in water. We only have one lone pair in the protonated alcohol. And we generate the carbocation. Okay? Yeah, okay, I went back. Sorry. And in the last step, I minus that we generated in the first or the second step, first step, sorry, is going to come in and attack the carbocation, and we're going to end up with a product. All right, so we should show every energy minimum. Okay, so this is here. And that's there. And it's required in a mechanism that we show all of the energy minima. Okay, so this is a good example of a mechanism equation. Right now there aren't that many possibilities. The mechanisms are going to be a little bit easier now than they will be in the future, but you'll be better at writing them, so it won't be that big of a problem for you. Okay, I'm going to pause the video here, and in the next one we're going to talk about this reaction right here, alkane halogenation.